Okay, so let us continue where we stopped. So as I mentioned with an example when we discuss this, where H is the decision tree and D is the training data label, wherein LC1 of H is the number of bits to describe the tree, right? So that is nothing but the description length of that tree, right? And similarly, LC2 of D given H is the number of bits to describe the training data D given the hypothesis H, right? So that gives us the meaning of what do we understand by this LC1 of H and LC2 of D given H, right? One important thing which has to be noted here, that is the LC2 of D given H is equal to 0 if the example classified perfectly by the H, right? So when we have the example which are perfectly classifying the hypothesis H, then in that case the LC2 value, that is LC2 of D given H, will be 0, and they need only describe exceptions, right? Only the exceptions need to be described. So with this understanding, when we again come to the same formula, that is the to compute the HMDL, which is the minimum description length MDL principle. Hence, uh, HMDL trade-off tree size for the training errors. Right? Hope you understand by this term that it is trading of the tree size, which is nothing but the length here, for the training errors. So when we have, let me describe this particular point here again, so that the next point is clear. That is, how do we trade off tree size for the training error, which is, in other words, when we have the length of the training, the described tree as 0, the, when we have this length as 0, when we have a perfect classification, right, which is of no error, there is no error. So when we have a training example which correctly classified, which is perfectly classifying a particular hypothesis, that means there is no error, then we can say that the length of the tree is 0, right? So this is what the trade-off that we are doing with the tree size and for the training errors, right? So if I have to put these things in the formula, the H map, which is nothing but the maximum a posteriori hypothesis, right? H map is equal to R max of the product of the hypothesis, the probability for D given H, plus the prior probability, right? Multiplied by the prior probability, which is P of H, probability for the hypothesis H, right? And when you apply the log on the both sides, the value that we get is an uh, arg minimum negative for the log to p given p of d given h, and again negative, that is subtracting the logarithmic value of the inferior or the the prior probability, which is p of h, right? So this formula here is again very important, right, which will be useful for us when we discuss the further topics, and also when we discuss the uh, important algorithms like naive Bayes classifier and Bayesian network, and also EM algorithm, right? So please make a note of these things, right? So one interesting fact that we need to know here from the point of the information theory is that the optimal code, right? The optimal code for an event with probability p is log to the base 2 p bits, right? So this is the optimal code which is already defined. So we don't have to worry about it. So why this? How do we say this is optimal? This is optimal because we have to consider the shortest expected coding length, right? We have to look for the shortest expected coding length, because we are defining on the grounds of the Occam's razor. And what does the Occam's razor says? It prefers the shortest hypothesis, right? Let me take you back to that slide. Yeah. So the minimum description length principle, as I mentioned, it falls on the ground of the Occam's razor, which says prefer the shortest hypothesis, and also the MDL principle, which is the minimum description length principle, also prefer the hypothesis H that has the minimum description length, right? So keeping those things in mind, the optimal code for us will be the shortest expected coding length, right? So when we have this shortest expected coding length, which is nothing but the optimal code for an event with probability p, is the negative of log to the base 2 p bits, right? So this is nothing but the length, right? There is nothing but the description length for that particular hypothesis. So let's interpret as one that minus log to the base 2 p of h is the length of the hypothesis h under optimal code, which is quite obvious, and negative log to the base 2 p of d given h, right, where d is the training data and h is the hypothesis. Then minus log to the base 2 p of d given h is the length of the d, which is the training data, given the hypothesis h under optimal code. Right? Hope the difference is now clear comparing these two lengths. Right? And as I mentioned, by considering the CAMS razor, here also in the MDL principle, that is minimum description length principle, we prefer the hypothesis that minimizes, right? So how do we have this minimized this thing? The length of H plus the length of misclassification, which is nothing but the length of that particular hypothesis H plus the length of misclassification. And how do we get this length is we have already seen in the above examples, right? So log to the base 2 p of h bits and minus log to the base 2 p of d given h bits. These are the lengths that we are going to compute. And when we ultimately sum up the length of the hypothesis h plus the length of the misclassifications, all the misclassifications that we have, that will have the minimized hypothesis is what we get. So we prefer the hypothesis that minimizes. Right. So this is all about the MDL principle that we saw. So a quick recap of before we wind up today's class. It's already time up, but a quick recap of what we discussed in the today's class. We discussed the maximum likelihood and the least squared error hypothesis, right? Where we discussed that under certain assumptions, any learning algorithms that minimizes the squared error between the output hypothesis prediction and the training data will output a maximum likelihood hypothesis, right? And then we discussed with learning a real valued function, right? We took an example, considering the example for the patient data, and then we computed the formula for that, right? And how do we end up having that formula? We saw the derivation for that. Then we discussed about the maximum likelihood hypothesis for predicting the probabilities, right? Predicting whether the patient, how much probability is there for the patient to be survived or no, right? We saw an example of that using the gradient search to maximum likelihood in a neural net, right? So we saw the example with respect to this and the background of the knowledge that we have with respect to the gradient descent search. And then ultimately we discuss the minimum description length principle, right, using an example. Right, so with this we come up to the end of today's lecture. If you have any doubt, you can ask me. The session is open. Let's say we have one more minute. Or else you can save your doubts and we can discuss the doubts in the next lecture, right? But again, let me repeat that whatever we discuss here, please make a note of these things and prepare your own notes. And these are very important from the external examination point of view as well. So these concepts is what we are going to use in the further algorithms in the lab, what we are going to see, right? So in the next lecture, we are going to take up lab experiment and we're going to be implementing these things what we have learned here for the algorithms like naive Bayes classifier and Bayesian network and also for EM algorithm, right? So please stay tuned and in the next lecture we'll take up experiment.